As a review for the gases that we learned from last year, we talked about all these different characteristics of gases. Gases expand to fill their container. The particles will spread as far apart as they can to fill the entire container. So when we're doing a problem, we can make the assumption that if a container size is specified, that's the volume of the gas. So if I say you've got gas in a 2-liter bottle, we can say that the volume of the gas is 2 liters. That's just an easy way to just solve the problems and work on those. Gases are highly compressible, which means that when you apply pressure, the volume decreases. You push in on it and it gets smaller. When you mix two gases together, they will form a homogeneous mixture. In other words, instead of staying separated, all the particles will mix in with each other until they're essentially the same distribution throughout the entire container. If you think back to the entropy demonstration with the red or the blue and the yellow flasks that mix together to make green, same thing happens with the gases. They'll mix together until they're the same, spreading out through the whole thing. Gases are fluids, which means they flow. The root word for fluid comes from flow, and that's because the particles move past each other. And gases have very low density. There's very little mass per unit volume. And all this happens because gas particles are pretty far apart compared to their individual size. If you look at just compare the diameter of a gas molecule to the distance between two gas molecules, we're talking about 1,000 times or 10,000 times or 100,000 times more space between them than their actual diameters. And in between is nothing. Empty space. Vacuum in between these gas particles. And so all of those characteristics are explained due to the fact that they have all this empty space. They expand to fill their container. Well, that's to fulfill entropy, right? The more spread out they are, the more spaces they're occupying, the greater the entropy, the more spontaneous that is. But they can also spread out because they're so far apart compared to each other's size that the forces aren't going to hold them together to make a liquid. They're highly compressible because of all that empty space in between them. You can increase the pressure, and they've got space to move into when you compress them. Same thing, they spread out into each other. Because they're so far apart, the particles don't interact. The one set of particles isn't going to stop the other from flowing. It might flow a little slower because it has to bump around a little bit more. But eventually it will form that homogeneous mixture because it has all that empty space to move through. They can flow because all that empty space, the particles just move right past each other without getting caught. And low density, there's all that emptiness in between. So it's like the difference between a styrofoam cup and a plastic cup of the same size. The styrofoam cup has much less density because there's so much empty space in that foam, the styrofoam, as opposed to plastic, which is fairly solid throughout. Now we define pressure as the force divided by the area. And when we're talking about gases specifically, we're talking about the force of the collisions of the molecules on the container walls. So if we take each individual gas particle, figure out the force with which it hits the wall, multiply that by all of the gas particles to find the total force of all the gas particles moving at their speeds inside the container, divide that by the area of the container walls, we can calculate the pressure. And in physics, the official SI unit for pressure is the Pascal, which is defined as a Newton, that's a force measurement, divided by square meters. Now Pascal, as it turns out, is a really lousy unit for pressure for chemistry because it's fairly small compared to air pressure. Air pressure is a lot larger than you think it might be. Every square inch of air pressure on your hand, if you just hold your hand up flat, a square inch on your hand is holding up about 15 pounds of air. And most people's hands are somewhere around 10 square inches. Well, that means if you hold your hand out, you're actually supporting somewhere around 150 pounds of air in the column going all the way up to the outside of the atmosphere. And I'm gesturing up right now, which of course you can't see, but I'm gesturing up. The column goes all the way up to space. That is about 15 pounds, 150 pounds of air you're holding up with your hand. And we're just used to that kind of pressure. Now, we as chemists like to kind of buck the trend, and so we've defined our own units for pressure. And the standard one that we use is 1 atmosphere. 1 atmosphere of pressure is the average normal atmospheric pressure at sea level. Kind of hard to define that because it's always changing, and how do we just define this one standard? Well, we use pascals. And someone just decided to set 101,300 pascals as standard pressure. So 1 atmosphere, normal pressure, is 101,300 pascals. So that's why pascals is such a lousy unit. 1 pascal is really tiny compared to the air pressure. Torricelli, of course, and we learned this last year, set up his dish of mercury with the tube in it, and the air pressure at standard air pressure is enough to push that tube of mercury up 760 millimeters. And so that's a unit we can use as well. 760 millimeters of mercury is standard atmospheric pressure. But some people don't like using millimeters of mercury as a unit of pressure because, oh dear me, that's actually a distance unit, millimeters. So they just changed the units to torr, T-O-R-R, after Torricelli. So 760 torr is the same as 760 millimeters of mercury, and that's standard atmospheric pressure. There's one on here that isn't defined yet, but I'll tell you right now, so you can write it down in your notes. 1 bar, B-A-R, which is, of course, short for barometric pressure, 1 bar is equal to 100,000 pascals. So 1 bar is a little bit less than 1 atmosphere, but it's easier conversion factor for pascals, and that's why some people like to use that. So if we take a look at 2 different devices for measuring pressure, on the left we have Torricelli's barometer, a dish of mercury, a glass tube that is taller than 760 millimeters, so usually just a 1 meter glass tube, closed at one end, open at the other, fill it with mercury, invert it, stick it in the dish, then take your thumb off. Atmospheric pressure is pushing down on the surface of the mercury in the dish, which of course will then push it up the tube. The mercury in the tube is being pulled down by gravity. And when those 2 forces have canceled each other out, the downward pull of gravity, the upward push of the atmospheric pressure, we can measure then the pressure of the atmosphere, the pressure of the gas in the atmosphere. We assume that the pressure, the force of gravity is not going to change, so really we're just measuring this relative to gravity. How far can it push it up against gravity? And it turns out mercury is 760 millimeters, or almost 30 inches, 29.92 inches. On TV, when you watch the weather report and they say, the pressure today is 30.1 inches, that's what they're talking about, this type of barometer. Now, of course, no one uses this type of barometer anymore. We have digital versions that measure the same type of thing. But we're always referring to a Torricelli barometer. If you want to measure the pressure inside of a container, we use something called a manometer, M-A-N-O-meter, manometer. And you can see that on the right. The tube at the top left there is connected to whatever container it is, and this is used for taking blood pressure. That'd be the cuff. The gas from that container pushes some dense liquid, usually mercury, down through a U-shaped tube and up another tube to the side. And the difference in the height is equal to the pressure that the gas is pushing. Now, if that manometer is open to the atmosphere, then you have to take the difference between the atmospheric pressure and that difference in height to find out what the pressure is inside the container. If it's a closed end, then it's 0, and so the height of the mercury in that tube is equal to the pressure inside the container. But of course we need to define some type of standard temperature and pressure that we're always comparing things to. And unsurprisingly, this is chemistry, we name things in the most boring way possible. We call that standard temperature and pressure, STP. Pressure, standard pressure, 1 atmosphere, or 760 torr, or 760 millimeters of mercury, or 101,325 pascals. The standard is the average atmospheric pressure. That's easy. For the standard temperature, we wanted something that was easy to work with in a lab, safe to work with in a lab, and easy to replicate everywhere. And the easiest way to do that is 0 Celsius or 273 K, the freezing point of water. Because if you have a container that's full of a mixture of ice and water, it's going to stay at 0 degrees Celsius until all the ice melts. So all you have to do to keep it at 0 degrees Celsius is keep adding more ice. The ice melts, add more ice. Ice melts, add more ice. And you're able to keep the container at 0 Celsius whatever glass jar you're working with for the pressure, just stick that into that ice water bath, and the temperature of the gas inside the container will stay at 0 Celsius, which is standard temperature. So very easy to work with. We use this to define the molar volume of gas. Molar is the adjective form of mole. So the molar volume is the volume of a mole of an ideal gas at standard temperature and pressure is equal to 22.4 liters. Later we're going to talk about what a real gas is, the difference between real and ideal gases. But for now, just know the molar volume of an ideal gas at STP is 22.4 liters. That's a little bit bigger than a basketball. So get that in your notes, get that memorized.